Our fourth subunit goes into the topic of outdoor air pollution in more detail. First, let's start by talking about the Environmental Protection Agency. The EPA monitors air pollution levels across the United States. It's an independent agency of the U.S. government that works to ensure that Americans have clean air, land, and water. It's responsible for setting and enforcing national environmental standards based on scientific evidence. Thanks to the EPA, data from more than 2,000 air pollution monitors across the United States is made publicly available. Here, we can see a picture of an air monitoring station, as well as a map identifying the location of these stations across the United States. These monitoring stations focus on 6 criteria pollutants as indicators of air quality. These usual suspects include sulfur dioxide, nitrogen dioxide, carbon monoxide, particulate matter of a certain size, ozone, in particular ground-level ozone that we'll talk about soon, and lead. Let's take some time to better understand these criteria pollutants. First, there's carbon monoxide, a colorless, odorless, and deadly gas. Potential sources include motor vehicles, cigarettes, and it's known to impact the ability of the blood to carry oxygen. Next, there's nitrogen dioxide, a reddish-brown chemical found in smog. Other sources include the burning of fossil fuels and industrial processes. It's known to contribute to lung irritation, the aggravation of asthma, and the reduction of visibility. Then there's sulfur dioxide, a yellow-brown gas commonly emitted from coal-burning power plants. It is known to contribute significantly to acid decomposition, as well as to breathing problems, property damage, as well as soil and aquatic life damage. The next criteria pollutant that we will examine more closely is the level of particulate matter in the air. A particle is a complex mix of extremely small solid and liquid components. A particle may contain many different materials such as combustion products, organic compounds, dust, pollen, etc. Particulate matter has many sources, including burning fossil fuels, agriculture, fires, unpaved roads, etc. Particulate matter is known to contribute to lung damage, asthma, and an overall reduced lifespan. Particles can range wildly in size. The designation PM stands for the measure of atmospheric particulate matter. The number following PM indicates the quantity of particles under a given size measurement. Specifically, PM 2.5 measures the quantity of particles smaller than 2.5 micrometers in the air, and a PM of 10 measures the quantity of particles smaller than 10 micrometers. We can see the size measurements compared to the size of a grain of beach sand on the right. PM10 typically includes particles of dust, pollen, and mold, while a PM of 2.5 also includes combustion particles, organic compounds, and metals. Tiny particles at the scale of PM 2.5 can penetrate deep into the lungs and cardiovascular system, increasing the risk of disease. This figure illustrates the penetration of differently sized particles into the human body. Larger particles at the size of PM10 typically only make it into the upper respiratory tract, and thus can typically be expelled easily. Particles at the scale of PM 2.5 can penetrate into the lower respiratory tract. Even smaller particles at the scale of PM1 can infiltrate the alveoli, leading to potentially serious problems. Furthermore, particles at the scale of less than 0.1 micrometers, otherwise known as nanoparticles, have the potential to infiltrate the entire bloodstream. Notably, sand particles blown into the air from dust storms in the Sahara Desert have been observed at even the nanoparticle scale. Here we further consider the potential health impact of particulates in the respiratory and cardiovascular systems. When you breathe in the fine particulates, they can travel deep into your lungs, causing respiratory problems such as coughing, throat irritation, difficulty breathing, asthma, bronchitis, and many other ailments. They can also cause heart problems such as heart attacks or irregular heartbeat. Lastly, with respect to particles, how long do they stay in the air? Gravity pulls big particles down out of the air faster than smaller ones. When these particles settle on a surface, it's called sedimentation. Many small particles can stay suspended for hours. In this table, we can see that ultrafine particles can stay in the air for weeks to a month, while fine particles at the scale of PM 2.5 can stay in the air for days to a week, and coarse particles at the scale of PM 10 can stay in the air for hours to a day. This makes fine and ultrafine particles even more dangerous, as they linger in the air for longer periods of time. Now we'll move on from particulates and identify the difference between primary and secondary air pollution. Primary refers to pollutants put directly into the air from a polluting source. Secondary air pollution occurs when primary pollutants combine with other substances in the air and create something more hazardous, for example, acid rain or smog. The sun often provides energy for these reactions. In this figure, we can see some of the primary pollutants we've already discussed up in the atmosphere, existing as a kind of chemical soup, and the sun energizes reactions leading to secondary pollutants. Now we'll take a moment to learn a bit more about some specific secondary pollutants. The first is photochemical smog, which is produced when ultraviolet light from the sun reacts with nitrogen oxides in the atmosphere. Photochemical smog is visible as a brown haze and is most prominent during the morning and afternoon, especially in densely populated, warm cities with a lot of motor vehicle traffic. In this figure, we can see an illustration of how photochemical smog is produced in a chemical reaction, again, fueled by the sun's ultraviolet rays. Our next secondary pollutant is industrial smog, which presents as a black-brown colored haze in the air that can be seen over some cities. It's composed of sulfur dioxide, small amounts of sulfuric acid, and suspended particles from the burning of coal and oil. Nowadays, it's mostly a problem in developing countries. The last secondary pollutant that we'll discuss is ozone, one of the criteria pollutants tracked by the EPA. Most likely you're used to thinking of ozone as that gas that exists in the stratosphere, protecting us from the sun's harmful ultraviolet radiation. That's the good ozone. However, there's also bad ozone that exists as a highly reactive gas with an unpleasant odor. It's commonly known as the smog of the troposphere. Bad ozone forms as a chemical reaction between volatile organic compounds, or VOCs, and the oxides of nitrogen from things like cars. Here we can see an illustration of the reaction that generates bad ozone, where primary air pollutants are emitted and rise up into the atmosphere, and ultraviolet light transforms the molecules into bad ozone as a secondary pollutant, that which then falls back down closer to the ground. Depending on a number of factors, the formation and intensity of air pollution can be modulated by a number of factors. For example, the local climate, with changing air pressure, temperature, and humidity that can influence the conditions needed for the generation of secondary air pollutants. Also, topography, in other words, whether there are hills or mountains nearby, or population density and the amount of industry, or the fuels used by the local population and industry for heating, manufacturing, transportation, and power, or the weather, in other words, does it rain or snow, is it windy, and are there tall buildings nearby or in the vicinity to slow overall wind speeds. So some of these items can serve to be protective against air pollution. For example, rain or snow can in a sense wash the air, as can salty sea spray on a coast. And winds can push pollutants elsewhere, making it someone else's problem, unfortunately. Thanks to air pollution legislation, many countries have put standards into place in an attempt to define safe limits for different pollutants as a benchmark for reducing pollution down to levels less likely to cause health issues. This table offers recommended maximum levels of different pollutants as set by different organizations and countries, including the World Health Organization, the European Union, and the United States. These numbers not only reflect the findings of scientific studies and recommendations by experts, but compromises between researchers and politicians attempting to strike a balance between public health safety and economic impact and the interests of industry. A more generalizable and public-friendly outdoor air quality index has also been developed to more easily communicate to the public current air quality levels in their area. Here, we see the color-coded air quality index ranging from good in green to very unhealthy in dark red, paired with recommendations for the public to guide their behavior and the precautions to be taken depending on the quality of the air. For example, when the air pollution is at a very unhealthy level, The following groups should avoid all outdoor exertion: people with lung disease, such as asthma, children and older adults, people who are active outdoors. Everyone else should limit outdoor exertion.